Okay, Shabab. Today, we are going to continue with the modeling, okay, by talking about, okay, solution of differential equation. If you remember, at the beginning of the course, we said we are going to do the modeling, and the modeling include the differential equation, transfer function, and later on, we will also take the state space representation. What we want to do in this lecture, okay, we will be talking about the solution of the differential equation. How do you solve the differential equation? I assume that you have taken the solution of the differential equation in math 202. Okay. Does anybody remember how do we solve a differential equation in math 202?
Yes, there are different methods.
There are different methods. You are absolutely right. What we are going to do here, we will add one more method.
Usually, Doctor, if it's an ordinary differential equation and it does not have a source response, we are just after a natural response. So we assume an exponential solution because, and then we will have a characteristic equation, and from that we can move.
ما شاء الله عليك عبد الرحمن، انت يعني زين، شكلك ما نسيت you don't shelf المعلومات من تخلص الكورس. الحمد لله. This is great. Okay. We will be doing, the solution for the differential equation, but a little bit different. I'm sure you are also familiar with it. But let me say the other thing which we want to do now. Suppose I have a system will be more than one input, more than one output. How do we find the transfer function for such a system? This is basically what we are going to do in this lecture, part of the lecture. Later on, we will be talking about something else, but at least the first part of the lecture, we will be talking about the solution of the differential equation, and we will be talking about the transfer function of multivariable system. Now, suppose I have, let's take an example. Suppose I have the following differential equation. What order of system we have in here?
Second order.
Second order. So in order to solve the differential equation, عبد الرحمن, please شباب, pay attention to the mic.
ايش يعني البقالة؟ انت جبت ايش تسوي؟ اذا جاتك
Doctor, I think you can mute all of them.
I already muted. I am muted. Okay. So basically, we have a differential equation. So we have the input. In order to solve the differential equation, I need to know the input and I need to know the initial conditions. Since it is second order differential equation, so I need two initial conditions. This is the y of 0 and y dot of 0, I must know. The input in here, it is r of t equal to 1, which is basically a step function. So, in addition to what you have learned in Math 202, we are going to use the Laplace transform. We are going to apply Laplace transform, okay, to the differential equation and to get the solution through the Laplace transform. I'm sure you have seen it. Maybe if you have taken Math 301 or I don't know, in Math 202, do they teach solution via Laplace transform?
No, actually, but we touched this in 207, I think.
Okay, so basically, suppose I will take. So basically, what I'm going to do, I'm going to apply Laplace transform for differential equation, move everything to the transform domain, then go back by doing the partial fraction and go and find the, find the time, because, ultimately the solution should be in the time domain. Okay, so let me take the Laplace transform of this equation. So I'm going to get the first term will give me what? What is
S squared y s
Square.
S square y.
Y of s, since I have initial condition minus what?
y0
No,
SY0.
the s
sy0
y of 0 minus y prime of 0 plus
that's it.
4s y of s minus 4y of 0 plus 3y of s equal to 2r of s. Now, let me substitute for the initial condition. Any question here? This is simply apply, the Laplace transform for the differential equation. So I'm transforming everything into the transform domain, into the S domain. And let me manipulate algebraically now. So y prime of 0 equal to 0. So I will have, let me keep s square, okay, the coefficient of s, coefficient of y, and this is y, and this is y. So it's going to be y plus 4s plus 3, this is y of s, equal to, in here I have 2 r of s plus, this is s times y of 0. Y of 0, we said it's equal to 1. So I'm going to have s in here. And this term, minus 4y of 0. So it's going to be plus 4. If I substitute for r of s, what's the transform of r of s? What is r of s?
Delta function.
No, r of s, this is r of t equal to 1. Laplace transform of the step will be what?
1 over s.
1 over s. So I will have s squared plus 4s plus 3 y of s equal to 2 over s plus 4. Or you can simplify it, and it will be, if we do that, if we do the simplification, we will have y of s equal to s squared plus 4s plus 3. And in here, I will have, let me go back. I will have, let me simplify this one here. The simplification will be what? S in the denominator, and I will have 2 s squared, s times s, plus 4s plus 2. Do you agree? This is the simplification of this part.
Yes.
Yes, yes.
So y of s will be, okay, in here I will have the s squared plus 4s plus 2, isn't it? Let me make sure. Yes. Okay. Now, this is in the S domain. I want to go back because the solution in the time domain. What do we do in here? How do we proceed?
Partial fraction.
Inverse.
Partial fraction. Exactly. This is equal to A over S plus B. Well, let me factorize this one. If you factorize it, this is going to be S
plus 3 multiplied by s plus 1.
S plus 1. So S plus 1 plus S plus, S plus 3.
And the up is c, right? Not s.
C, yeah, C.
This is C.
Just a constant.
Thank you. Okay. Let me find A. What's A? How do I find A? A equal to what?
-1.
A will be y minus 1, no?
Why did the usual way, Doctor?
By
We just
S, you eliminate the S in here and evaluate at 0.
2/3.
2/3. So this is equal to 2/3s plus, how about B? B associated with the 1, so I eliminate the 1 in here. Okay, so I will have minus 1 times 2, that will be minus 2. In the numerator, in the denominator, B minus 2 in the denominator, and in the numerator I will have 1 and minus 4, okay,
minus 1.
minus 3, plus 2, minus 1. So it's going to be
1/2.
half S plus 1, and then you can do the same for the third one, S plus 3. C will be equal to, eliminate this one, sorry, eliminate this one, not, okay. So I will have minus 3 in the denominator.
And minus 1 in the numerator.
In the numerator what?
Minus 1.
In the numerator 9, minus A, yes. Minus or plus? No.
Minus.
should be minus 1, minus 1.
No. Oh, 3, yes, 3 will be minus 1. Okay, minus 1 in the numerator. How about denominator?
Will be 6.
6. Great, thank you. So minus 1/6. This is in the transform domain. Now I can, invert individually.
Step response, and also you have some exponential because of the shifting.
If,
Yes, yes, right.
so
I'm
this
saying
is
just,
basically,
yeah.
the first term will give you step, the second term will give you exponent, and the third term will give you another exponent, where those are the roots of the transfer function. Any question here?
Don't we multiply it by the step, Doctor?
Okay, you are absolutely right. Or you can write this, the solution will be valid for t greater than or equal to 0. You are absolutely right. Technically, yes, we should multiply it by a step function. Or
This is the definition of transfer function.
greater than, the solution will be valid for t greater than or equal to 0. Okay, now, how about if I want to find the steady state in here? What is y steady state?
Yeah, t goes to infinity.
So t will go to infinity, and that will give me
2/3.
2/3. Or I can find it from here by using the initial value theorem. You know what's the initial value theorem?
Doctor, sorry, but what do we mean by steady state?
Steady state, it is when the times become very large and the system will either, in this case, the system is stable and it will reach, it will reach certain value. You let the system run for long time. That's where steady state.
Yes, now I get it.
Okay, look, but you reach the steady state if your system is stable. If the system is unstable, for example, if I have in here the exponent in the 3t, as t goes to infinity, well, basically we don't reach steady state. It's going to be infinite. But okay, we are using steady state where the time go to infinity. I can, as I said, I can get the same result by you applying the initial value theorem. That's basically y of s, y steady state equal limit as s goes to 0 of s, y of s. This is the same as y steady state in here, which we are limit as
t goes to infinity
of y of t. Okay, so they are the same. So if we apply this theorem, we are going to get, again, 2/3. which will be the same result. We will be using the final value theorem little bit later. Okay. Any question here?
Yes, doctor.
Yes.
We transform it to the S domain and then back to the time domain to remove the differential equation, or?
Exactly. So we are going from the differential equation in the time domain, convert the differential equation into an algebraic equation. Okay, so this is in here. If you look at this one, this is nothing more than algebra. It's an algebraic equation. I can manipulate it easily. Then I go back to the time domain, avoiding, the forced solution and the homogeneous solution. So it is, it will be, it will give you the same, it will lead to the same result. Okay?
Okay, very clear. Thank you, doctor.
Okay, so basically, as I said, we are giving another way of solving the differential equation by using the Laplace transform. What we want to do next, this is basically if we plot the response, and this is what we are going to get. Now, as I said, the other objective of this lecture is to give the transfer function for multivariable system. In this case, I have one current source, but I need the transfer function between the current source and V1, which is this one, from here to here, and V2. Okay?
We have to make the equivalent circuit. We have to, right? So
okay.
The
use
inductor
node
and
voltage.
the C2, we have to combine the two.
Well, this is one approach. Great. Okay.
We have to find the equivalent
just one second. Shukran Abdurrahman. But let me ask, okay. Nader Al-Harthi. Al-Harthi.
Yes, doctor.
Great. Is there any other alternative? نادر شكلك المرة الماضية please make sure that when the class finish you leave.
كنت موجود بس آخر وقت فصل النت علي.
كيف يعني أنت everybody left أنت وخلينا نشوف الثاني فراس حسين. فراس. Are you there فراس؟
Yes, doctor.
ما أدري اثنينكم أنتم ما أدري يعني شكلكم تحبون اللكتشر so much. انتهت وانتم ما شاء الله عليكم.
لأنه آخر كلاس دكتور، بعض الأحيان الواحد ينسى يسكر.
الله يكون بالعون. الله يكون بالعون. Anyway, Abdurrahman suggested we do the transformation. Is there any both of you, any one of you? Is there any other way of doing it? First of all, look. أول حاجة, first of all, let's change the elements into impedances.
Right.
It's going to be SL. How about this one? What is this going to be? 1 over?
C.
C2.
C2S. Yeah, 1 over C2S. And this one is going to be 1 over
C1. Yes.
S. And the R will remain the same. Again, as I said, Abdurrahman, he suggested one method. Is there any other alternative, of finding the relationship between V1 and R, V2 and R? And
can we use nodal analysis?
You are absolutely right. I think nodal analysis in this case is more appropriate. Who is that?
Salam.
Salam?
Abdus Salam.
Abdus Salam. Abdus Salam. Great. So, in this case, the most appropriate method will be the nodal analysis because of the structure of the circuit. Okay, so Abdul Salam, why don't you apply KCL at V1? At
minus RT, R of T.
Okay.
V1 over 1 over S C1S.
So V1 over C1S.
1
which
over
is going to be
S.
C1S, isn't it? Because
Yes.
it's dividing plus. So the current
V.
Okay, plus.
V1 over R2.
Great. Plus.
V1 minus V2 over R1.
This is equal to R of T. You said it's minus, so I just put it in the other direction. Thank you very much.
R of S, Doctor.
Okay.
Doctor, R of S.
R of S, you are right. Thank you. Thank you. So this is one. How about the other one? Any volunteer for the at node 2?
Yes, Doctor.
Okay, go ahead.
V2.
V2.
C2S.
C2S plus.
V2.
Okay.
Over SL.
Okay, great.
V2 minus V1 over R1.
Equal to 0. Great. Thank you very much. I really appreciate it. Okay, Shabab. الحين, now we have two equations. Okay. How can we solve them? Because I need V1 to R and V2 to R.
From the second equation.
But before we proceed, of course, you, okay. Sorry.
From the second equation, Doctor, we can express V2 in terms of V1, and then we substitute in the first equation.
So what you are suggesting, Abdurrahman, you are suggesting we do elimination.
Yes, exactly.
This is one way of doing it. Okay. So basically, if we, write what I have put in here neatly, this is what you have. And you are suggesting, Abdurrahman, we will eliminate one of them. We substitute. Okay. Can we do it a little bit differently? Let's do it a little bit differently. Okay. What you are suggesting is perfect. Okay. It's perfect. But what I'm saying, okay, let's look into another one. Let's write this one in a matrix format, where I have I need V1 and V2 are my output, the unknown, and R is the known quantity. So let me put it in a matrix format. In the matrix format, what will be the coefficient of, what will be the elements in the, first of all, okay, what dimension of this matrix is going to be?
I think 3.
2 by 2.
2 by 2.
2 by 2.
2 by 2, yes.
So the first element will be, what's the first element will be? The coefficient of V1, which will be C1S plus, okay,
1 over 2.
R2 plus
1 over R1.
So 1 over R2, 1 over R1, okay. And in here, minus 1 over R1. What about this side?
RS.
RS.
RS. Now in here, I will have, from the second one, I will have minus 1 over R1. And in here, I will have C2S, okay, plus 1 over SL plus 1 over R1. And this is 0. Do you agree?
Yes, this is more neat.
What?
This is better in terms of...
Well, it's an alternative way. Now, the question is, how do we solve this matrix now?
Find the inverse.
By inverse. By inverting what you are suggesting, okay, we can invert this matrix. Okay, that will be great. Perfect. Shabab, by the way, I hope you know how to invert at least 2 by 2 matrices. How do you invert matrices, Shabab?
We take first of all the determinant.
On the determinant.
Okay.
And then we modify the main matrix by swapping the main diagonal entries and take the negative of the off diagonal, or the the secondary diagonal. I don't know.
This is perfect. Perfect. Shabab, you have to know at least the 2 by 2. Maybe because sometimes look in quizzes and exam, maybe we'll ask you about to invert matrices of 2 by 2 or sometimes 3 by 3. Even though 3 by 3, if we ask you, there must be certain trick in it because the time, I mean, it's time consuming. Now, again, so we can solve the system by, inverting this matrix. So basically what we are saying, it looks like we have, let's say this is matrix A and this is X equal to Y, where A is this matrix, X is this vector, and Y is this one. By inverting, so basically what you are suggesting, Abdurrahman, basically I will have X equal A inverse, and I am assuming the system is invertible, multiply by Y, and you can get the solution. Is there any other way of solving the system? Any other suggestions, Shabab?
Using algebra.
Yes, I mean, Hadi, what's your name?
Khalid.
Khalid. Algebra, yes. What algebra? Did you hear about Kramer's rule?
We make the diagonals.
No, not derivative. No. Kramer's rule. Did anybody of you remember Kramer's rule?
This
The
is
bunch of equations, right?
No, not differential equation.
from secondary school. This is one way to solve the.
Look, in Kramer's rule, basically, if I want to solve for the first element, V1 of S equal to the determinant of the matrix A, okay? And in the numerator, I'm sure, look, I thought in the prep year they give you this. They didn't give you this one?
Yes, we took it, but we forgot.
We have also taken it in secondary school even.
Okay.
Yeah.
Right. Then in here, what we will have, we replace the first column by R of S and 0 by the known column, by the known quantity, and I will have minus 1 over R2, sorry, minus 1 over R1, I think. Okay, and
C2S
1 over SL plus 1 over R1. Or R2. No, this should be, I think this should be R2, isn't it?
Well, Doctor, I think.
No, it's R1. It's R1. Okay, and then you get the answer. V2.
What about the denominator, Doctor?
Okay.
Denominator.
The denominator will be the determinant of this matrix. Determinant of A, let's say, where A is this.
Okay.
Again, this is determinant of A. However, now, what do we have?
C1S plus 1 over R1.
Okay,
R2,
C1 S plus 1
over R2.
R1 plus 1 over R2. And in here, I have minus 1 over R1. In here, I will have R of S and 0. Let me put it neatly. This is the matrix. And this is what I'm saying. Okay. So, in this case, you can find the determinants and then get the answer. If you do that, this is what you are going to have. You know, what you have suggested, some of you, Abdurrahman suggested, okay, in the elimination of the variable or matrix inversion, all of them, they will give you the same answer. It is an alternative way of doing it.
Yes, I think the matrix format will be helpful when we have a large system, when we have,
exactly,
for example,
exactly.
We have n number.
If you have, exactly, if you have three equations, then the element
Right.
is going to be, you know, tedious.
Exactly. Yes.
Might lead to, you know, mistakes. Well, this is systematic way. So basically, what we have in here, you can write the V of S in a matrix format. Okay, let's say G of S, R of S, where the G is going to be, okay, let me call this one G1, 1, and this one G2 and 1. So I will have G11, G21, R of S, and this is V of S. This is in a matrix format. The transfer function, when you have multivariable, the transfer function is going to be a matrix in a matrix format. Depending on the dimension of the matrix, it depends on how many input and how many outputs. The number of row will be the number of the output, which is in this case, I will have 2 by 1 because I have 1 input and 2 outputs. If I have two input, then it's going to be 2 by 2 and so on. Any question here?
طيب Doctor, how can we find the time domain of this one right now?
Okay, simply all what you have to do. What do you want to find in the time domain? What are you looking for?
Transfer.
No, this is the transfer function in the transform domain. In the time domain, you mean that you want the impulse response.
Yeah.
Okay, if you want the impulse response, okay, suppose in here, this is a little bit complicated because of the variable. Suppose they have values, all those constants have values. So it's going to be an algebraic equation, okay? Do partial fraction and invert and go to the time domain. If you want to get, suppose what I'm saying, suppose, you know, suppose C2 equal to 1, suppose all the elements are equal to 1. So the first one is going to give, the second one is going to, or the first one is going to be V1 of S over R, of S equal, if my parameters C1, L1, and R1 equal, and R2 equal to 1. So it's going to be what? S
plus 1 over S plus 1.
S plus 1 over
S plus 1 plus S plus 2.
Okay, simplify. Okay, simplify and, you know, do partial fraction and invert. You can do that if you want to.
Or I can put that in MATLAB and find the inverse.
Or you can do it in MATLAB. You are absolutely right.
Okay.
Okay. Right.
Doctor?
أيوة.
كان في point you said we have 2 outputs or something like that. I didn't understand it.
If you have, okay, suppose, okay, let's go back to the, suppose in here, let me inject in here, let's say, let me put, let's say I put a voltage source in here. What do you call it? Let me call it VS. Source. This is plus or minus. How many input I have in this case now?
You have 3 now source response.
You have 2 inputs. The R.
Oh, yes, 2 inputs.
So if I have 2 input and I have 2 outputs, what I'm saying, okay, my transfer function G of S, which relate the output to, the input to the output, this is multiplied by the input, okay, and this is V of S, okay. I have in here 2 input and in here I have 2 outputs. So the matrix is going to be 2 by 2. This is what I meant. Is it clear?
Doctor, if it was 3 outputs, what will change? It will be 2 by 3?
You tell me what will happen. What's your name?
Majid.
Majid. Abdurrahman. what will be the size of the matrix if I have 3 output and 2 input?
Again, Doctor, the question.
What will be the size of the matrix if I have 3 output and 2 inputs?
Maybe 3 by 2.
3 by 2. 3 by 2. Look, the matrix, okay, this matrix will be number of output by number of inputs. So the matrix could be square or could be, you know, not rectangular.
Basically, the number of inputs we have to match the number of sources.
Exactly.
Because the inner entry have to be the same, so the multiplication will hold.
Yes. Okay. Excellent question. Please, if there is any more question, I'll be more than happy to answer them. If I don't know, I don't know. I'll try to figure out next lecture. But shoot any question. And definitely we have the class, mashallah, is, you know, very active, and, you know, people can help. Okay. Any other question? If there is no question, let's move.
By the way, Doctor, for the numeric inverse and the calculator that we have, we can do the inverse for the 3 by 3.
Definitely. Okay. Let me go to the other topic. Okay. Now, again, go back to the beginning of the semester. We said we are going to study, okay, the modeling of electric circuits, okay, mechanical system, where we took the spring, for example. And we said also we are going to deal with the electromechanical system. So now we would like to talk about the DC motor. Okay. We would like to control the DC motor. The DC motor usually it has 2 inputs, field and armature, and we'll come and explain. So today we would like to, you know, find the transfer function which relate the output of the DC motor to the input. Some of you have taken 360, and in there, how many did anybody take 360? I cannot say how many of you, because I cannot see your hand. Of course, we can do polling. Okay, anybody took the 360?
But it was a kind of saving, memorizing.
Okay, so we have at least 2 people. Okay. Who raised his hand the first? I think Zuhair, I don't know.
Yes, me, Doctor, in the previous term.
Okay. So basically, in 360, what you have taken in there, you have taken the internal, what structure of the DC motor and how does it operate. In here, what we are going to do, we would like to model the system. We would like to look at it from input-output point of view. Okay, so sometimes the system will get stuck. Okay, now, what's a DC motor, by the way? What is
coil
a
and
DC
a magnet.
motor? What?
A coil and a magnet.
A coil and a magnet. That's all? What does it do? It's definitely, it has a coil and magnet. But what does it do? What's the function?
Converts from mechanical to electrical.
Shukran, Abdulsalam. Yes, it converts electrical energy into mechanical energy. Okay, so that we can drive an external load, let's say. I'm not converting for the sake of conversion. I would like to use it. Okay, now how does it operate? How do we do that? Suppose I have, this is the structure of a motor. Now, in principle, how can I convert the direct current into a mechanical energy? What do we do?
By magnetic induction.
By magnetic induction. So basically, if I will have two magnets that will interact with each other, okay, then I can have a motion. So I need two magnets. The first magnet, let me put it what we call in the stator. And this is the stator, the stationary part of the motor. By the way, okay, where's the application? What are the applications for DC motor? Where do we use it in real life?
Machines like the washing machine and all this stuff.
Okay. What else?
Cars.
Very simple. And, you know, in every house.
Toothbrush.
Servo motors.
What?
There's an application called servo motors.
But no, I'm asking much simpler.
بلندر.
تويز شباب. معك اخوانكم الصغار ما عندهم تويز. How does toys they operate?
السيارات الكهربائية الكتريك فيكل.
الكهربائية yes بس على الأقل what I'm saying, yeah, the easiest thing is the toys. All the toys
yes.
have DC motors. Definitely there are a lot of application. Okay, toys part of it لكن بصورة عامة definitely it has many applications. Okay, now let's go back to in here. What I need a magnet. So this magnet, either I can do it in the stator, either you know, I can have a permanent magnet, or if I have a winding and I pass a current through the winding. In here we are going to, you know, talk about, you know, magnetic field coming from passing a current in the coil of the stationary part of the motor, which called stator. So if I pass a current through the winding, I produce magnetic field. Let me have another winding in here, in the rotor, and I pass a current. What will happen? You have another magnetic field. So if you have two magnetic fields, what will happen between them?
They will oppose each other and start rotating.
Exactly, they repel each other and they start rotating. We will come to in a moment or maybe next lecture and explain that. But let me convert this one into a circuit, into a mathematical model. Okay, let me model first of all the stator winding. How do I model the stator winding? Any suggestion?
Voltage source.
Resistor and
okay. Exactly. Why resistor? You are absolutely correct. Why resistor?
The resistance of the wire.
Exactly. شكرا يا خالد. The resistance of the wire or the heat conversion. So basically I will, you know, have, this is the model. Let's say VF, R, and L, SL. Okay, so this will give me IF, the field current. Now, let me go to the rotor part. What will be in the rotor part?
معلش دكتور.
Again, an applied input, let me call it VA, and then let me call this RF. Okay, F, the field. So I will have RA, SLA. What else I will have?
The voltage induced.
Exactly, because what happened, you have two, okay, you are rotating a coil in a magnetic field that will produce certain voltage. We call it the back EMF. So I will have a voltage in here. And the direction of this voltage is going to be opposing what I am having. So this is a plus and minus. And then whatever that will be, I will take this one, okay? I will take this one through the shaft and connect it to a load. So what's my output will be? What is the output?
Voltage.
What?
It will be a torque, doctor.
Torque? Yes, torque. But you know what? I'm driving a load. So what do I measure in the load?
The rotation speed.
The rotation speed or the position, either theta or omega. But of course they are related because theta, the derivative of theta equal to omega. So look, this is the, let me put it in a neater way. So this is basically the circuit which will model the system. And I'm looking at theta, the output, let me, okay, of S, over either VF or VA. Okay, or VA, which is the voltage here. Of course, I cannot, take them simultaneously because in that case, I will have nonlinearity. So I will take one at a time. If I fix VA, I call my system field control DC motor. If I fix VF, I'll call it armature control DC motor. Any question here?
عيد النقطة هذه يا دكتور.
What I'm saying in here, I'm interested in the transfer function between output, which we said, let's say theta, and input. I have two input in here, VA and VF. We are going to see through the derivation, at one point in time, IF and IA, they will multiply each other. So that will give me a nonlinear relationship. In order, the transfer function is valid for linear system. So I have to fix one at a time. If I fix IA or VA, then the control will come from varying VF. In that case, we call it field control DC motor. Or, if you remember at the beginning of the lecture, I said, field control DC motor, it means that the armature, okay, the armature, okay, voltage is constant, VA is constant. And the other one, the field control is constant. Okay, the field control or the field voltage is constant. So the control will be from the armature in this case. Okay. Any question?
Is there any advantage from fixing VF or VA or?
Yes, as I said, we will come a little bit later in the derivation. At one point, we have the torque developed equal certain constant time IF, IA. When you have the multiplication of the two, you will have nonlinear system. The transfer function model is valid for a linear system. So I must fix one at a time.
take the superposition دكتور ولا؟
كيف؟ No, not superposition. Well, but no, in superposition, you are assuming one of them equal to 0. No, you cannot, cannot have one of them is 0 because, you know, there will be no magnetic field in that one. If you
I see. So the idea is that we assume that the two are not varying at the same time.
Yes, you take one at a time.
No, Doctor, I'm asking if there is any advantage of taking VA as a fixed value instead of VF, and the opposite.
Okay. It depends on the application. It depends on the application, and we are going to see the order of the system is going to be different, depending on which one you are taking. It depends on the application, Yebni. Okay, each one has its own advantage and disadvantage, but we are going to study both of them.
Okay.
So all of these just are applications, right? I mean, we apply the same principle once we go to the model, the circuit. So we have the same principle. So the question that might arise in this case, in the exam, or I don't want to be exam oriented, but this is, you know, a usual question that do we expect a system in the exam that is we have not seen before, and we have to remember the laws and all this stuff, or it will be a direct application of what we have studied? You know, we have a model, and that model is a circuit or what have you.
شكرا عبد الرحمن على الكونسيرن. ولوك شباب، احنا دائما مشكلتنا نفكر كيف ناخذ الجريد بالاكزام. بالنسبه لي I think what's important is how do you understand it. What we are going to see next, okay, it is simple KVL application with, again, combine it with the Newton's law. So I think you will know, the only thing maybe by common sense, look, by common sense, what we are saying, for example, in here, if I have, شباب اللي يبغى يترك المحاضرة fine, okay, the time is over, but I will continue. Look, in here, I have, you know, two fields, okay? Two fields, okay? So that will give me, you know, the two field interact will give me certain, you know, certain torque. The torque will be proportional to what? The intensity of the magnetic field, which is the field depend on the current which you are putting in here. So, you know, some of them, what I'm trying to say, if there's any formula, I will give you the formula. You don't have to memorize. No, I don't assume that you will memorize anything, but at least you should understand. But if you are talking about, you know, a formula in an exam, usually
not the formula, Doctor, really, but for example, the model of the DC motor, you know,
it will be, you know, variation of this model. It will come in different mode. For example, in here we are going to derive this fully in the S domain. Later on, we are going to talk about the state space. One time, I brought exactly the same question, same derivation, however, to state space. It is not out of the space. It is within what we study in here, but in different formulation. Because look, I don't think it will be wise to give you set of questions, memorize them, and come to the exam.
Yeah, of course, yes.
So basically, and at the same time, look, in here, we are trying to help you. We don't have, you know, ma'raka. We don't have, yani, challenge always. It's what's important is that how can we transmit this information to you and how can you understand? The goal is not to flaunt people. I think, you know, if the rate of, you know, of passing is low, I think that will be failure from the instructor point of view, okay, side. So look, but at the same time, you cannot make it trivial. So you have to strike a balance. Usually in the exam, you try to strike a balance between the two.
Yeah. So just my point, Doctor, writing models from a problem, from a design problem, for example, a DC motor or what have you, to the circuits, to the resistors and capacitors. Sometimes it's not straightforward. You have to remember the things that you have taken in previous courses. But for this case, since we will explain and we